In the last episode, we cut text into tokens and turned each one into a number, and we ended on a problem. The model knows the token for king and the token for queen, but those numbers are just labels, like jersey numbers on players. Jersey number 9 and jersey number 10 tell you nothing about whether two players are alike. So, how does a machine get from a meaningless ID to something that actually captures meaning? That somehow knows king and queen belong together, and that a cat is closer to a dog than it is to a car? The answer is one of the most beautiful ideas in all of artificial intelligence, and it is called the vector embedding. Quick note before we dig in. If you find this useful, subscribe and drop a topic you want explained in the comments. Now, let us get into it. Here is the whole concept in one sentence. A vector embedding is a list of numbers that captures the meaning of a piece of text as a point in space, so that things with similar meaning sit close together. That is the trick. Instead of giving each word a single arbitrary ID, we give it a long list of numbers, maybe a few hundred or a few thousand of them, and we treat that list as coordinates. Just as 2 numbers can place a point on a map and 3 numbers can place a point in a room, a list of hundreds of numbers places a word at a precise spot in a vast invisible space of meaning. We cannot picture hundreds of dimensions, and that is fine. The math does not care how many directions there are. What matters is one simple, almost magical consequence. Words with similar meanings end up near each other in that space, and words with different meanings end up far apart. Let me make that concrete. In a well-trained embedding space, the points for cat, dog, hamster, and rabbit all cluster together in one neighborhood because they appear in similar sentences across the training data. Off in another part of the space, car, truck, bus, and motorcycle cluster together. The model was never told that a cat is an animal or that a truck is a vehicle. Nobody labeled any of it. The structure emerged on its own purely from the patterns of how words are used. And that is the deep insight underneath all of this, an idea from linguistics that says, you shall know a word by the company it keeps. Words that show up in similar contexts must mean similar things. Embeddings are that idea turned into geometry. Now, for the result that made people sit up, back when this first became practical with a system called Word2Vec around 2013. Because each word is now a set of coordinates, you can do arithmetic on meaning itself. Take the vector for king. Subtract the vector for man. Add the vector for woman. And the point you land on is almost exactly the vector for queen. Read that again because it is genuinely strange. The machine has captured the abstract concept of royalty, and separately the concept of gender as directions you can move in. The same trick works for Paris minus France plus Japan, and you land near Tokyo. It has learned the relationship of a capital to its country as a direction in space. No human wrote that rule down. It fell out of the geometry, and it was the first clear proof that a computer could capture not just words, but the relationships between them. So, if meaning is distance, how does a computer actually measure how related 2 pieces of text are? It measures the angle between their 2 vectors, using something called cosine similarity. Do not let the name scare you. The idea is just this. If 2 arrows point in nearly the same direction, they are closely related, and the score is near 1. If they point in completely unrelated directions, the score is near 0. If they point in opposite directions, the meanings are opposed. So to ask how similar are these 2 sentences, the computer embeds them both into vectors and checks the angle between the arrows. That single number, that similarity score, is the quiet workhorse behind an enormous amount of what AI does. And this is where embeddings stop being a neat party trick and become genuinely useful, because they unlock semantic search. Old-fashioned search matched keywords. If you search for how to fix a slow laptop and the helpful document said speed up a sluggish computer, keyword search would miss it entirely because not a single word matched. Semantic search does not care about the words. It embeds your question into a vector, embeds every document into a vector, and finds the ones whose arrows point the same way. It matches meaning, not spelling. So it knows that slow laptop and sluggish computer live in the same neighborhood, even with 0 shared words. The same machinery powers the recommendations that say, if you liked this, you will like that, by finding items whose vectors sit close to the ones you already enjoyed. It powers clustering, where you dump in thousands of customer reviews and let them group themselves into topics nobody defined in advance. Meaning becomes something you can search, sort, and measure. I want to be precise about one thing, because it is the bridge to a lot of what comes later in this course. There are two related but different jobs here. A dedicated embedding model has one purpose. You give it text, it gives you back one vector that captures the meaning of the whole thing. That is different from the chat model that writes you paragraphs. They are cousins, both built on the transformer we will dig into soon, but tuned for different work. In practice, you use real, named embedding models for this. From OpenAI, there is a family called Text Embedding 3. Cohere and a company called Voyage make strong commercial ones. And there is a whole world of free open-source models you can run yourself, the most popular coming from a library called Sentence Transformers. With small fast models like the one nicknamed All-Mini-LM that run happily on a laptop. Hold on to this idea of turning a whole document into one searchable vector, because it is the exact foundation of retrieval augmented generation, the technique for grounding a model in your own private data, which gets its own deep dive later in the series. Embeddings are the bedrock that the entire RAG pot of this course is built on. So how does this look depending on who you are? As an individual, you brush against embeddings every time a Notes app lets you search by what you meant rather than the exact words, or a photo library finds every picture of a beach without anyone tagging them. As a startup, embeddings are often your first real AI feature and the cheap one. You run your help articles or your product catalog through an embedding model once, store the vectors, and suddenly you have semantic search or smart recommendations that would have taken a team months to build by hand. And as a large enterprise, embeddings become the way you make a decade of scattered internal knowledge findable. Picture a bank with millions of documents across a dozen systems. By embedding all of it into one shared space of meaning, an employee can ask a plain question and pull back the relevant passage from a contract written years ago, no matter what words it happened to use. That is enormous leverage, and it rests entirely on this one idea of meaning as coordinates. So let us bring it home. An embedding turns a piece of text into a list of numbers, a point in a vast space of meaning, where closeness equals similarity. That single move lets a computer do arithmetic on concepts, measure how related two ideas are with the angle between their arrows, and search by meaning instead of by matching letters. Tokens gave the model something to read. Embeddings give it the beginnings of understanding. But notice we have been talking about meaning in a kind of frozen, one-shot way, one vector per word or per document. The real magic of a modern model is that it weighs your words against each other live in the moment, and to do that, it has to hold a certain amount of your conversation in mind all at once. There is a hard limit on how much it can hold, and when you cross it, things break in surprising ways. That limit is called the context window, and it is where we go next. That is the core of it. If this helped, hit like and subscribe, ring the bell for the next deep dive, and tell me in the comments what you want broken down next. Thanks for watching.